Welcome back to another video. My name is Michael. I'm the founder of Buffalo Performance and Analysis, where we combine sports science, strength and conditioning, and sports performance to give coaches the tools necessary to build the next level of elite athletes. In today's video, we're using R to create a logistic regression model to analyze injuries and illnesses in soccer athletes. So to get started, we're going to install the necessary packages. The main three that we're going to use are tidyverse, dplyr, and this last one, the report function. Now, a logistic regression is used when we're trying to analyze the probability of an event happening. So today we're trying to analyze the probability of an athlete being injured. But when we're looking at the data here, we can't really utilize it when it's in this yes and no character format. So what we need to do is recode our injury and illnesses into binary ones and zero. So to do that, we're going to create a new data frame, call it df1. We're using the mutate function, calling on injury illness, and we're going to use the if else function. So if injury illness is equal to no, it's going to return 0, and if injury illness is yes, it's going to return 1. When we run these lines of code here, and then we view the data frame, we see that the only difference that occurs is now our injury illnesses are in ones and zeros. So once we've recoded our variables, now we need to find what metrics matter. So to do that, we're going to use the core.test function, and that's going to allow us to do something called the Point Biserial Correlation, which looks at the correlation between a dichotomous 0 or 1 and the continuous variables that we're going to be looking at. So we're going to look at the relationship between injury, illness, and RPE. When we run this line of code here, in the console below, we see that it gives us our t-value, degrees of freedom, and our p-value. We do have a really small p-value, and then it also gives us the correlation coefficient here of 0.17, so we know that it's a really small correlation. Another cool way that we can look at the core.test is we can name it. So if we name the second one, just calling it B, and then we use the report function of B, when we run these two lines of code here, this makes it a lot more easy to understand and to read. It's going to walk you through everything. It's going to show you that the correlation between injury, illness, and sleep duration, it's negative, that it's statistically significant, and that it's small. And then it gives you the R value here, and then it also gives you your P value down here at the bottom if it's less than 0.001. Run our core tests for all our variables. We see that RPE has a small correlation with injuries and illnesses, so does sleep duration. Now, sleep quality, soreness, and stress all have medium correlations with injuries and illnesses. So we know that we're probably going to be using sleep quality, soreness, and stress in our model, but what we need to do next is check for collinearity. To test for collinearity, we're going to use the core.test function again, and we're going to cross-reference our internal metrics to make sure that there's no collinearity. So when we do that, we're looking at RPE and sleep quality. There's a small correlation there. Sleep quality and stress, there's a large correlation between sleep quality and stress. Between sleep quality and soreness, there's a small correlation, and between RPE and soreness, there's a large correlation. So we see that sleep quality and stress are strongly correlated, and that due to collinearity, we're going to exclude sleep duration and stress from our multivariate model. So we know that we need to include sleep quality, soreness, and RPE into our multivariate model. Before we create our multivariate model, we're going to just take a look at a simple logistic regression. So we're going to call this one Model 1. We're using the GLM function, and we're looking at the relationship between injuries and illnesses on sleep quality. Our data frame is df1, and the family is binomial. So when we run this, and then we look at the summary of Model 1, we're going to take a look at our coefficients here. So we're really interested in our p-value here as well as our z-value. So we see that our p-value of less than 0.05 means that it's statistically significant, and we can confirm this with the z-value or the z-score of negative 3.157, And we know that anything outside of 2 standard deviations from the mean, so either +2 or -2, is going to confirm that it's statistically significant. So we see that -3.157 is outside of 3 standard deviations away from the mean. Taking a look at these numbers can feel daunting, but what's really great is using this report function here. If we report model 1, it's going to walk us through everything. So it's going to let us know that they fitted a logistic regression to predict injury illness with sleep quality. And then it walks you through the formula that it used. And then it tells you right here that the model's explanatory power is moderate. So sleep quality had a moderate effect on injuries and illness. And then it gives us a pseudo R squared of 0.19. Now the pseudo R squared is also the coefficient of determination that ranges between 0 and 1. Then it walks you through the statistics of the model as well. And it tells you right here, the effect of sleep quality is statistically significant and negative. And then it walks you through kind of the confidence intervals and the p-values down at the bottom. So with all that being said, what this model really tells us is that sleep quality has a moderate effect on injuries and illnesses, and that we have a pseudo R of 0.19, and that we need to include other internal metrics to our model to better explain injuries and illnesses. We want to try to get our pseudo R squared closer to 1. That's going to be a better fit of our model. So now that we've done our simple logistic regression, now it's time to add more variables and try to create a better fit of our model. So this next model we're going to look at, model 2, is looking at sleep quality and soreness on predicting injuries and illnesses. So when we run this line here and then call on the summary here, we're looking at our p-values again. So we see that soreness is statistically significant, and again that z-value is outside 2 standard deviations. However, because of a slight collinearity, we see that our sleep quality is no longer statistically significant. It's just above that 0.05 threshold, and we can confirm that it's right in front of our 2 standard deviations. So when we run the report function here for model 2, we can see here that we do have a pseudo R that is a lot larger, but because sleep quality is no longer statistically significant, it lets us know that right here. The effect of sleep quality is statistically non-significant and negative. And then we see here the effect of soreness is statistically significant and positive. So it lets us know that even though sleep quality and soreness combined better predicts injuries and illnesses, that sleep quality is no longer statistically significant. So because of that, we're going to try to create another model where our variables are statistically significant. So in this model, we're going to look at the injuries and illnesses. We're going to use sleep quality and RPE as our variables here, and we're going to try to make sure that sleep quality and RPE are both statistically significant in our model. Running these lines of code here, our p-values both look good, and so do our z-scores outside of 2 standard deviations. And then we run the report function of model 3, and we can see that our pseudo R squared here is of 0.48. So our previous model was 0.62, but sleep quality was no longer statistically significant. So this one is a little bit less of a better fit. It's still considered substantial, but it's a little bit less of a fit than our previous model. But we see that both sleep quality and RPE are statistically significant, and so that's what we're really after. But let's take a look at one last model. We know that sleep quality and RPE in the same model, our sleep quality is no longer statistically significant, but we want to try to make a model that is the best fit. So we're going to mess around with this one here. We're looking at sleep quality, RPE, and soreness. We know that not all of our variables are going to be statistically significant, but let's just take a look at how good of a fit we can create. So calling on model 4 and the summary of model 4, sleep quality is not statistically significant. RPE is not statistically significant, but our soreness is. And again, we can confirm that with our z-scores here. And then when we run our report for model 4, we're really interested in our pseudo R squared. So we see that the model's explanatory power is substantial in predicting injuries and illnesses, and we have a pseudo R squared of 0.47, or 74 rather. And so that's extremely substantial. With 74% accuracy, we can predict injuries and illnesses based off of sleep quality, RPE, and soreness. However, like we just said, sleep quality is no longer statistically significant, and neither is RPE. It's an interesting thing. We found our best fitting model, but the values or the variables aren't statistically significant. And so what that means is that maybe taking a look at it post hoc after the fact, we can kind of explain why injuries and illnesses occur. But if we're trying to build a predictive model using values or using variables that are not statistically significant historically is not going to be the way to go when we're trying to forecast injuries or predict future injuries. So it's important for sports scientists and data analysts when we're creating a logistic model that we're looking at metrics that matter, and when we're creating a multivariate model that all the variables are statistically significant. If you like this video, please leave a thumbs up. Thanks.